15 students that are, we are recording. And the 15 students that are sitting here in front of us today have worked incredibly hard this semester. We have been able to travel through amazing parts of the country. And throughout this, the students collected data with us, not just on some of the long-term research that OTS does, but they also worked with different scientists in Mapungubwe, Hamakuya, Cozy Bay, as well as the Drakensberg. And today kind of caps off this semester because each year for our capstone project, we provide the students with a theme that aligns with sandparks management and some of the research needs that they have. But this year is pretty special because not only did we go to new sites and we got to see the beautiful Drakensberg and Cozy Bay, but our students actually had 3 different research themes. Today, there's going to be 2 presentations looking at bats in and around the Skukuza rest camps, and not just Skukuza, but the Kruger National Park rest camps. And then there is going to be a group that's going to be looking at grass and their fire adaptations. They were actually so inspired. This wasn't a theme originally, but they were so inspired by some of the work that Gareth Hempson did with them in the Drakensberg that they are continuing that work. And then we're also going to have a group that is going to be looking at the rare Adenium swazicum or swazi lily and some of the drivers that are causing its decline. So for everybody online, I hope you guys can hear us. We are going to start. And I'm going to call up the first presenters, who's Santi, Julie, Laura, and Molly. And they're going to be talking about bat box effectiveness and the bat species composition that you see in rest camps in the southern part of Kruger National Park.
Okay. Hello, everyone. My name is Laura, and I go to the College of the Holy Cross.
I'm Santi, and I go to Cornell University.
I'm Julie, and I go to Wheaton College.
I'm Molly, and I go to Hope College.
And today we're going to be talking about bat box effectiveness in Kruger National Park rest camps. Okay, so it has been brought to our attention that the bats in Kruger National Park rest camps have become a problem, and they're causing concerns for the tourists in the area. So there have been a lot of complaints, both online and to reception, regarding the the bats in Kruger National Park. And the reason is that these bats are moving into the accommodations and causing a smell typically associated with bat poop or guano. And this is causing a concern to the residents of these accommodations, especially when they're near potential kitchens or other areas where they are frequenting. It also can be a concern with human health, as bat guano can also carry some fungal diseases. Okay, so a little introduction on bats. So in Southern Africa, the IUCN categorizes 15% of the bats in Southern Africa as data deficient. And this is really important to our study because we really need to find out more information about what bats we have in Southern Africa, and more specifically in Kruger National Park. So previous to 2021, there were very few studies in Kruger at all. And then in 2021, there was a comprehensive study done in the north of Kruger National Park. And we got a lot of information about what bats are in the north of Kruger National Park. However, in the south of Kruger National Park, kind of where we are in Skukuza today, we did not have a lot of information about what bats or what the bat demographics kind of look like. So that's kind of what prompted our study. Bats aren't always bad. Bats also are a form of pest control. So in these rest camps, this can actually be really important, especially when they're around bodies of water that have a lot of insects. Specifically, mosquitoes can be a problem, especially when they carry disease. So bats can act as a natural control method for these insects. Bats, when they are not flying around at night, they participate in roosting behaviors. Typically, crevice roosting bats will roost in tree bark, tree crevices, or small rock crevices. However, with the increased encroachment of humans into spaces where bats typically occupy, there are bats that are now moving into human spaces, such as in these rest camps that we see bats roosting between the wall and the roofs. So this is becoming a concern, especially with tourism. So as a management strategy, a lot of people have been using bat boxes as an alternate roosting strategy to encourage bats to move outside of the human accommodations and move into bat boxes. And these are typically moved away from human spaces so that the smell, the presence isn't bothersome to humans. Instead, they can have their own roosting space away from humans. So it causes less of a concern and decreases the human bat conflict. There are different types of bat boxes. In Kruger, we mostly see the pole-mounted bat boxes. There can also be ones mounted on houses, as well as different sizes for different species of bats.
So in order to conduct our study, we worked alongside Sam Park's Biodiversity Conservation Manager, Stephen Midzi, to tackle the bat problem and to help with potential management solutions, as well as to build upon that 2021 study that was conducted in the north of the park. We used that study's results regarding species presence and echolocation data in order to guide our own study. And we sought to answer two questions. How does bat box presence influence species composition in rest camps? And how does bat box presence influence the occupation percentage in camps? Question, we conducted visual surveys and used bioacoustics to identify occupation and species at each camp. Visual surveys were done at houses in 4 rest camps: Kakuza, Bergendal, Lower Sabi, and Crocodile Bridge. In our study, we looked at specifically whether bats were occupying houses or not. However, the next group after us will expand more upon this. So we use bioacoustics to identify what species were present in the bat boxes and around the accommodations. So for a little bit of background on bat bioacoustics, bats have a high echolocation frequency, and we can identify these sounds by using softwares like Kaleidoscope, which can present these sounds visually. This is important because echolocation calls are usually beyond human hearing capacity, which is at 20 kilohertz. And the minimum and maximum of these frequencies can be used to identify different bat species. Down below, we have a spectrogram, and the x-axis is time in seconds, and y-axis is frequency in kilohertz. This is mostly what we were looking at when we were identifying the bat species. The louder sounds are represented by brighter colors, and in this one, it would be like the brighter green. And the red line represents what humans can't hear above. So we also used audio moths to collect this data, and they were used as an audio recording device. We distributed 5 audio moths at each rest camp and put 2 on bat boxes for the camps that had bat boxes. We recorded overnight and analyzed 1 minute of calls every hour using Kaleidoscope and the species call library from the north of the park to identify and compare species from the north and the south.
All right, some quick summary numbers. We surveyed a total of 313 houses across all 4 camps and noted 205 bat roosts on the way. These bat roosts were not distributed equally across all houses and camps. One house in particular had 44 bat roosts. It was just all the walls all the way around. Lower Sabi is the bat champion of camps. It had the most bats, bat species, bat roosts, the highest number of bat occupancy, everything. Every single pole-mounted bat box that we checked was occupied by bats, although the building-mounted ones were not. We analyzed 285 minutes of audio recordings for a total of 12 bat species representing 3 families. Now, the other bat group is going to go a little bit into more detail about the houses and the camps, and we're going to focus on the species and occupancy. So this graph shows the 6 most common bat species. The other 6 are lumped into the other category. Across all 4 camps, the counts are the number of minutes in which a species was detected. So you can see that the 3 free-tailed bats that are highlighted were detected most frequently across all 4 camps, along with the African yellow bat was our other most common species. You can see that Lower Sabi had a lot more bats detected than every single other camp, and Bergendal had the fewest bats detected. So these are the 4 main perpetrators, the root of the problem. And we can dive into a little bit of the species-specific factors here. The little free-tailed bat, Egyptian, and Angolan free-tailed bat are all in the family Mollusidae, and they're pretty similar. The little free-tailed bat is the smallest one. I think it's really cute. But these 3 bats, I think, are generally more the problem. Their guano is the one that smells quite bad. The African yellow bat is a lot larger, but it's not necessarily the source of as many complaints. And switching over to occupancy, this graph shows, again, the 4 rest camps and the percentage of units occupied at each rest camp. You can see that the camps where the bat boxes are present have much lower occupancy of the houses overall. And now we can combine the information about the species and the presence of bat boxes to make more informed management decisions.
Yes, so bat boxes in the camps was the original strategy for giving them a place to go after they were evicted from the guest accommodations. And this helps in the short term, but they quickly overpopulate the bat boxes. Each one can only accommodate 500 bats. And then they need to find additional roosting space, which means they go back to the houses. And Sandparks is addressing this by scheduling translocation to similar ecological areas. And eventually they plan to remove the bat boxes entirely. This does not fix the overall issue because by the time they're removing the bat boxes, they've already roosted in the houses again, and they're already, they're already multiplying in the houses again. And this is what's been observed at Lower Sabi, which is the only camp that has had its bat boxes removed. And we propose replacing the bat boxes, the full bat boxes with empty bat boxes when they seem to be close to reaching capacity to prevent them from moving back into the houses. And especially before moving the occupied bat boxes to a different location. This allows the bats left behind to still have a place to roost and not have to find their way back into the houses. And we additionally recommend using different types of bat boxes. As Laura mentioned earlier, bat boxes are highly species specific. And there's only one type currently in the camps. And the Angolan free-tailed bat is the biggest of the 3 free-tailed bats, and it's bullying out the smaller ones. And it's the smaller little free-tailed bat and Egyptian free-tailed bat that we are seeing visibly like roosting around the edges of the houses when we did our visual surveys. So implementing the rocket boxes pictured on the screen, they allow higher concentrations of bats as opposed to the flat ones currently there. And then different size openings for the smaller bats to keep out the larger, to make that more specific and give the little ones a place to go. We hope that our work here on species composition and bat box alternatives help make management decisions in the future. Thank you.
Thank you so much, guys. We're going to open the floor to questions. We're going to give the audience the opportunity first, and then everybody online, you can type out your questions, and then Sia will be reading that to you. Does anybody have questions?
Hi, guys. That was a nice presentation, but I remember in your results, you said that the bed boxes that were mounted onto buildings were not occupied. Were they mounted onto the houses?
They were not mounted onto the houses. They were mounted onto reception and like places in busier areas that bats tend not to frequent anyway, just because there's too much human activity. And Bergendal is the outlier that the next group will cover in a lot more detail.
Okay, so sorry, I just have a quick question also. How far are the bed boxes from the houses?
Again, that's part of the next group study question, and they will cover that in more detail.
Thank you.
Great presentation, and also a really vexing issue. There are all kinds of rumors floating around what sandparks are going to do with the bats. So it's nice to hear what you guys are up to and what they've done. I've got two questions. One is a theoretical question. The other one's a practical one. The theoretical one is, your data suggests that these bat communities don't reach any sort of density dependence because of availability of food, but rather occupancy of available habitats for roosting. Have you read elsewhere in the literature or from elsewhere in the world where, the hope is that you can provide enough accommodations, if you will, that eventually they'll reach some form of density dependence because of availability of resources? And then also curious about wet-dry cycles. I don't know if you've heard anything about that at all.
Yeah, in terms of wet-dry cycles, we didn't find anything crazy in our research. There honestly hasn't been a ton of research regarding bat boxes and when they will eventually reach like a capacity for the certain environment that they're in. In general, it's a very understudied field. But yeah, the general idea is that, especially when we're moving these bat boxes out of the area, the idea is that by providing new habitats for them in the empty bat boxes, the idea is that you're not having them in the residential areas. But yeah, I guess if you did build enough bat boxes, hypothetically, you would reach some sort of maximum level. But with Lower Sabi, they had 46 bat boxes, and they were all removed because the bats got completely out of control. So it's hard to say.
I guess what's really good about your data is we can keep doing it at the same time of the year, even into a dry cycle, and see if we see similar patterns.
And the other thing is that with these bat boxes, what we really need is some long-term studies. It's completely lacking in what happens past a year or two after implementation.
Yeah. And then quick practical question. How do you move the bat boxes with the bats in them?
They do it during the daytime, is my understanding, when the bats aren't active, but that is, I think, beyond.
When we did go to Lower Sabi surveying, we found the remnants of where the bat boxes were removed. So we could see that they had just been cut and moved. Yeah, but you can still see the like holes in the ground that were cut. Yeah, and the pile of guano is still there. Yep.
Hi guys, nice presentation. I was just wondering if you had a look at bat box designs, because I do know that you do usually get a smaller bat box and then you get a colony box, which is for the much larger groups. And from what we've seen around the camps, it looks like they're the much bigger boxes. Do you think this would have an effect on kind of their breeding, or whether or not you're getting as many bats, or, how they move?
I think, sorry, can you repeat the question? Sorry.
So basically, do you think there would be any impact if you change the design of the box to smaller boxes rather than the very large boxes, or no?
No, I think bigger boxes is the way to go, just because of like size restrictions, like in the camps, like it's pretty hard to put up a ton of bat boxes and have them not interfere with guests. So I think more in a box as possible is like the right way to go. And also in previous studies that were done, not all bat boxes do become occupied. And I think if you have a box that is occupied, like it's just easier to get more in that one box rather than playing around with trying to get a bunch of smaller colonies established.
Thank you.
Thanks, guys. I was really interested to see some of that occupancy data with the surveys you did. Can you just talk a little bit how did the surveys work? You mentioned 300 houses surveyed.
Yeah, so we worked a lot with the other group, and I'm sure they'll get into this more. But we basically went together to all the breast camps and we split up into groups, and we each like picked like different locations to survey. We walked around the outside and looked for different like signs of occupancy. And they'll repeat this again, but like for an example, like whitewash or like the amount of guano, stuff like that.
And from what you saw, do you think these are pretty persistent roosts, or do you think they're changing from sort of weekly or nightly basis where the bats are on?
There were some camps that it looked like they were just like hanging out and they were gonna fly in, just not permanent. But definitely in like Lower Sabi and some of the other camps, like in Skakuza, there were a lot more like signs of permanency.
We also did find that the species of the free-tailed bats, the family Molosidae, they tend to be like they go back to the same sites. Like they will stick to a spot that they're in, which is I think also why there's more of a problem. They have a high fidelity to their roost. So I think that the ones that we're seeing tend to stay. Yeah.
Awesome. Thank you. And then one last thing, any thoughts on that lower occupancy in Skakuza relative to?
Yeah, the other team is going to talk a little bit about more the house structures and why that might differ between camps. But yeah.
Great. Thank you, guys. Nicely done.
Thanks. That was a great presentation. A couple of quick questions. One is I noticed that some of the photos that you showed had the bat boxes out in the open sun. And I'm just wondering if you found anything in the literature or you were able to observe anything in differences of where the bat boxes were actually located in maybe their abiotic environment.
Again, the other group is going to touch on the abiotic environment a lot more. But from what Stephen told us is that they don't seem to care how warm it is. In fact, they like the warmer environments. They can breed a lot faster. South Africa is the one place where bats have been noted using torpor or something similar to allow their body temperatures to rise further than what other animals can handle.
And also the rocket bat boxes that I was talking about, they seem to be generally preferred by generalist species because of the shape that they are and like how they're built allows the bats to kind of self-regulate their temperature based on where they are in the box. So it's less of a danger to them if it gets too hot or if it's too cold, they can self-regulate.
Thanks. And then kind of related a little bit, you guys mentioned the word pest a few times and used some quotes from people in the park. Is there an education campaign as well, at these sites, showing the real benefits of bats?
Not that I'm super aware of, like we didn't come across that, but we did actually note that some of the reviews for a lot of those were for Lower Sabi, which as you can see through our results had more of a bat occupancy rate. But at some of the other camps, there were people commenting when I would search for reviews that said bat. It was like, oh, like we really liked watching the bats. Like it was really cool seeing the bats going in and out of the bat box at night. So I really do think it depends on the person and the severity of the problem. When they're just going in the bat boxes and separated from human space, they tend not to be an issue. But I think the other team talks a little bit about education as well at the end of the presentation.
Thank you.
Yeah.
Thank you. See, are there questions online?
Okay, the first question is from Zingfang. He's saying, talking about moving bat boxes, is it possible that the distance from resource sources is a driver for the return of the bats to the houses in the camps? And then he's explaining. So even if the boxes are moved, the bats still return to the camps because it's easier for access or distance to resources.
Yeah, it's definitely possible. A lot of the camps that we surveyed happen to be right around rivers, and rivers for our insect-eating bats also tend to mean more insect populations. So high food availability near the camps is preferred. Also, we found in our literature that some specific species like the little free-tailed bats actually have shown preference for the accommodations like these in comparison to natural spaces. So they're actually preferring to live in these spaces rather than living in the tree bark in the rock crevices. So yeah, it is possible depending on, I guess, how far they're moved.
I think the hope with translocating the occupied bat boxes to super similar environments would help with that. And then as to distance, the next group is also going to talk a bit about that.
Okay, the second one is from Olivia Hoffman. The question is, do you know anything about the cost to put up or move or replace a bat box? Would it be costly? Would it be cost effective for the park to continue constructing bat boxes?
So we don't know anything about the cost of these management decisions, but what we have heard a lot about is the cost for the park to deal with tourists who are the impact that this has on tourism in the park, where they have to give out a lot of refunds and tourists are not very happy with the accommodations they're living in. So there is some opportunity cost if we don't do anything about that.
Okay, another one is from Zing Fang. Is it possible that building bat-proof houses in camps will be a solution that can be coupled with bed boxes? So this prevents bats from occupying houses while giving them alternative roosting sites.
Sorry, Zingfa, the next group will also be covering.
Okay, the last question is from Levi Lilienthal. So the question is, did you do any work looking at suitability of bed boxes as a habitat in cases where both bed boxes and cabin are available? Do beds have a tendency to pick one of the other or houses or that are more suitable?
It's talking about the free-tailed bats, specifically the little free-tailed bats, which we notice to be more of the problem in Lower Sabi, have high roost fidelity and will return to their roosts wherever they establish it. So if that's in the bat boxes, then they're going to go back to the bat boxes.
Does anybody have any more questions? And then thank you so much. It's a fantastic talk. Next up, we have Lily, Janet, Margaret, and Lucia, and they are going to be telling us how accommodation characteristics might be influencing the patterns of bat activity at these different camps.
Hello, my name is Lily. I go to Cornell University.
Hi, I'm Margaret and I go to Colby College.
I'm Lucia. I go to Vassar College.
And hi everyone, I'm Janet and I also go to Cornell University.
So we also looked at bats. Uh-oh. So we specifically looked at how different characteristics of accommodation infrastructure might influence bat infestation patterns, specifically intensity and frequency within rest camps in Kruger National Park, in Southern Kruger National Park. And we looked at the same rest camps as the previous group, so Bergendal, Crocodile Bridge, Skukuza, and Lower Sabi. So we went around to the houses and we would, as was kind of mentioned before, we would split up into groups and we would go around each accommodation unit and we would measure the intensity as one of our infestation patterns. And so we rated the intensity from 1 to 3 based off of different characteristics of bats that were present. So for example, a rating of 1 could be some whitewash and some discoloration, as well as perhaps the presence of guano. A rating of 2 could be perhaps stronger discoloration and the presence of a single bat. And then a rating of 3 meant that several bats were visible and there was extensive guano, whitewash, and wall discoloration. And so the accommodation characteristics that we looked at for each unit was canopy cover, which was done through observation on the ground. So we would go around a house and we would estimate how much of the percentage of sky that was present over the roof. We also looked at building heights. We also looked at roof types. So there were 3 roof types present in the camps, and they were distributed differently. And we'll go into that. One was thatch, one was tiled thatch, so it was tiles on top of thatch, and then one was corrugated iron. We also looked at different types of walls, and there was brick, so there was exposed brick and plastered brick, as well as concrete and canvas. And then finally, we looked at the distance of each accommodation unit to the nearest bat box or river if they were present.
Starting off with Lower Sabi, we had 3 main types of accommodations. These were the 10th, which had canvas walls and corrugated iron roofs. It's worth noting that recently the ceilings were removed due to tourist complaints about infestations, which can be seen here, which is why it looks so weird without a roof, about a ceiling. Next, there's the larger bungalows, which had concrete walls and thatch roofs, as well as these smaller bungalows that had plastered brick walls, as well as thatch roofs. Over here is a map of Lower Sabi showing all the different accommodation types. On the top is the tents, which, as you can see, lower infestations, lower intensity. And here's everything else. A lot of red, a lot of infested houses. So 45 of the 70 accommodations that we surveyed were infested. As the other group mentioned, this is the highest proportion out of any camp. And the factors that we found were driving infestation occurrence and intensity were, as well as number of roosts, were wall type, roof type, building height, and canopy cover. Starting off with the building materials themselves. In terms of roof type, thatch had the greatest amount of infestations as well as the greatest infestation intensity, greater than corrugated iron and greater than the single tiled thatch building that we surveyed. Furthermore, concrete wall types had the greatest number of infestations and intensities, followed by plastered brick and then canvas. As you can see, corrugated iron and canvas tended to have the lower infestations. These were the tents, as mentioned previously. Okay. Next, looking at building height, shorter buildings tended to be more likely to be infested. Pretty much all here. And then for canopy cover, for every 20% increase in canopy cover, the number of roosts in a single house increased by 5.
So next we're going to talk about Skakuza. So there were 3 main types of accommodations there. Bungalows that had plastered brick and then a thatch roof, bungalows with, again, the same sort of walls, but then tiled thatch for the roofs. These are some of the newer ones that have been constructed more recently. And then riverside bungalows, which had the concrete type walls and thatch roofs. So within Skakuza, we found that 74 of the 162 buildings we surveyed had active bat infestations. As you can see, the black dots represent buildings that we did not survey. Those were either occupied by people or, in the case of the large cluster in the middle, there's active construction going on. And then, so the factors we found that influenced the intensity and frequency of infestations here were the roof material and canopy cover. So the 2 roof materials were the tiled thatch and the regular thatch. And again, similar to in Lower Sabi, we see that the thatch roofs are more frequently infested. than the tiled thatch. However, there was not a real difference in the intensity of the infestations in Skukuza. And then looking at canopy cover, interestingly, we see the sort of opposite trend where there are more roofs in the buildings with less canopy cover. So this is different than what we saw in Lower Sabi. And the higher intensity ones tend to have less canopy cover. So this trend is definitely different from what we saw in Lower Sabi. And this shows that these patterns may really vary between the different camps and different ecological factors.
And the third camp we looked at was Crocodile Bridge. At Crocodile Bridge, we surveyed two types of houses. The first one being a bungalow where you have a concrete wall and a thatch roof. And we also surveyed one staff house, which also has a concrete wall, but the difference was that it was much bigger than the bungalows we were looking at, and it also has a corrugated iron roof. And interestingly, what we found was that none of the variables we looked at was correlated with infestation rates or intensity. We did find 8 of the 22 houses that we surveyed infested, but relatively compared to Skukuza and Lower Sabi, the intensity of infestations was much lower than what we've been seeing at the other 2 camps. And then finally, our last camp we surveyed was Bergendal. Here, it was a bit different. The wall type that we were looking at was exposed brick with thatched roofs. As you can see on the picture to your right, I believe, a lot of the thatch roofs also had a lot of mesh that was protecting it. And so interestingly, we found that there were no bat infestations within the houses at Bergendal, but all of the bat boxes, as the previous team has said, were all occupied. And so that leads to the question is, what's different here? So as I mentioned previously, the bat boxes were occupied. We also noticed while we were going out and surveying that they were holes within the mesh that I showed you a picture of previously that looked like that they had been occupied by either squirrels or monitor lizards, which suggests that they are either competitively excluding bats or predating on them. So we think that's what's happening in Bergendal.
So some of the implications for future management, one is we found that building materials more consistently predicted infestations than landscape characteristics like canopy cover and distance from rivers. So for building materials specifically, in terms of both intensity and frequency, concrete tended to have more infestations or be correlated with more infestations than canvas in the wall types, and for roof types, thatch generally had more correlations with infestations than tile thatch. We found that in general, the distance of an accommodation unit to a bat box was insignificant. It didn't show any correlations to infestations. And then finally, as was kind of mentioned before, there's a lot of construction ongoing. And so it could be taken into account that these different building materials may be important, as well as shifting to less permeable materials, such as for the roofs. And also ceiling gaps in thatch could potentially help the problem.
And so circling back to why this is such an important issue, we have to realize that while dealing with problems like this, it's important that we take a holistic approach, because while we know that you have a lot of tourist complaints that the other group was talking about, on one hand, that is affecting the tourism that Kruger National Park sees, but on the other hand, there's also concerns over bat welfare. While we were doing a lot of surveys, especially in Lower Sabi, where we had the highest intensity of infestations, we saw like some dead bats within the mesh. And so this is overall a problem that needs a multifaceted approach, and it's complex. And I think that there's multiple factors at play here. So on one hand, while we have to take care of the welfare of bats, we also can work on shifting the public perception through engagement opportunities. And I think we did see this at Bergendal. There was a little sign that was telling people about the bats. So this is already in play, but focusing more on this would be good, because one of the main complaints that visitors have with this is that they're worried about the disease risks that this may pose, but literature has shown that in reality, the risk is very low with visitors who are coming through. So in conclusion, a One Health standard is going to lead to good, ethical, sustainable management.
And then overall, summarizing what both groups have just talked about and our future recommendations that we have for sandparks. Firstly, diversifying the types of bat boxes used because different species are known to inhabit different types of bat boxes. So making sure that you are having a broader reach with placing different types of bat boxes, as well as when we're removing these bat boxes, ensuring that the bats who are left behind always have alternative roosting sites available within these camps. Because you have to recognize the fact that even if you are taking out these habitats with the bats in them, there are still going to be some left behind who would go in and inhabit these houses. And then retrofitting and maintaining existing structures. So as I showed you previously, there was a picture of the mesh that was covering some of the roofs. What we've noticed is a lot of this has been degraded. So just making sure that these are being frequently maintained and going through and checking those. But yes, thank you so much for listening to our presentation about bats. Does anyone have any questions?
Much, guys. Fantastic talk. Are there any questions?
Anybody has any questions?
Again, great presentation. It's a tricky proposition. So the one confounding factor, I guess, is that the tents at Lower Sabi are much younger than the other buildings. So there might be a sort of a fetch length effect. But that doesn't detract it away from your data.
I think
So I've been sitting here pondering why Skukuza and Lower Sabi have such a high density of bats in the camps, whereas Bergendal is somewhat different it's a vastly different landscape and it's some distance from the river. Croc Bridge is very close to a river, but you could argue it gets hotter in summer. But the previous group said, well, heat is not likely to have such a big impact. So I started thinking about not only species pool effects, but also abundance across the landscape. So the one neat way to think about this is to start monitoring bats outside of these camps and get some sense of the abundance in the landscape. So there's no doubt that vegetation structure influences bat communities. You've read it all. You've seen the data that open versus clutter edge bats. You see this great change in distribution across the landscape based on the density of trees. So have you guys read anything about other work looking at communities of bats in this landscape, whether there might be some sort of species pool effect going from the basaltic landscapes to the granite landscapes? You've spoken a lot about the effects of rivers. I'm just pondering about the broader determinants of bat distribution and abundance. Under the bus.
So there's in Kruger National Park specifically, there is honestly not a lot of research on bats and about what's influencing them. I'm sure there's some knowledge of like the ecology of different bat species and what their preferences are ecologically, but with regards to especially with
they're still talking on bats
camps and human encroachment
I don't know who
specifically.
she is.
I suppose savannas in Southern Africa overall, there's not as much literature. But so that is definitely something to consider, I would say, in future and future research. But
I have a thought now. When we were one of the interesting articles I came across, not necessarily within Kruger, but it was a paper I think somewhere in Europe that was talking about bats within the same species itself, depending on the landscapes. Landscapes might not be the right word. Habitats that it is inhabiting have different preferences. So even if it's within the same species, maybe they prefer like higher versus lower roost heights. And I think that was one of our explanations for why like some of the trends we're seeing, for example, with canopy cover, was the opposite within two camps. So I think that based on our recommendations, it is very camp specific, and maybe there is like a explaining factor that we haven't looked at yet overall. But I think from what we've been seeing is that it's very camp specific.
So just one last thought also. I mean, you guys have done engage in pretty exhaustively bit of work here. So another way to think about this is setting up an experiment. So how would you set up an experiment to test some of your ideas?
That's a great question.
I feel like how you were mentioning earlier with the tents and how they were more recent, you might need more long-term data in order to best assess this. But like the other group was talking about moving bat boxes, that's something that can be done as long as you have long-term data. And you could also experimentally change roof types or seal the brick or seal the thatch and see what happens. Yeah.
The other group also kind of mentioned how there was a little bit of work that was being done in the northern part of the park. And so perhaps also creating some kind of comparative work would be important.
I was thinking you could maybe just set up like 2 or 3 different roof types, put them at different heights all along the river, and you just test to see outside of camps what might happen. And then the last thought that struck me is, of course, there's lots of artificial light, these insectivorous bats. Maybe that offsets the whole argument about availability of roosts versus insects. It's a fun question. Good luck for next year's summer.
Are there any other questions?
I tried to do
Online?
Yeah, thanks, guys. That was really cool to see. I think it's going to be hugely useful a bit of work for basing decisions on going forward. So really nice to see. I agree with you that the solution needs to be sort of mechanical or physical, and that the problem is largely driven by this new infrastructure. So, yeah, it was other than the mesh, were there any other interventions that you came across that had been trialed or implemented in some of the buildings? I know you obviously explored different building types and building material, but did you see any other interventions other than the mesh that had been trialed?
For one, there's in some accommodation units, they tried to seal the gaps of holes that were created. And so there were a few like implementations like that.
So in Bergendal, I think you might be able to see in this picture. So normally where the thatch sort of meets the wall of the building, there are sort of these like gaps between the thatch and the building. And so here you can see that there's like concrete bricks, it looks like, that are sort of filling that gap. And so that seemed to be pretty effective at sort of filling that like peak roosting spot. Because normally they would be against or the vertical surfaces.
Oh, they tried to keep
so that seemed like it may be a
spruce,
promising
is that it?
option.
Yeah.
And then in the tents in Lower Sabi,
Don't blow that
there
away.
was, so you have this tent and then there's a metal roof over top of it. And in a lot of places, the sides where that gap was between the tent roof and then the metal roof, there would be mesh sealing those openings so that they can get in there. So those seem to have some promise for decreasing.
And it was interesting to see, so you found a different relationship with canopy cover between the different camps. Because I was thinking that might just be related to age, that actually in these, you have a higher canopy cover in older buildings.
Yes.
More recovery of the vegetation.
We suspect that that is part of it. In Lower Sabi, the tents did tend to have lower canopy cover.
It's just more recent clearing.
Yeah.
Cool. Thank you, guys.
So the first question is from Levi. You touched upon this briefly, but what are some land use biotic factors that affect bat distribution in Kruger National Parks or elsewhere?
So we largely looked at within the rest camps, because there is sort of a lot of these sort of ideal places for them to roost. We did notice just anecdotally that underneath bridges is a very popular place for bats to roost. And then Stephen was saying that sometimes there will be so many bats in certain areas that you'll find them like roosting just like on dense grasses and things because there are just so many of them. But it would definitely be interesting to look more at some of those landscape level factors.
Also, we do know that you tend to have a higher abundance of bats closer to rivers. So that was a reason why we're looking at distance to river, but we found that that had no significant impact on the level or intensity of infestations we're looking at. And we think that's because all the camps we're looking at were within like a really close range to a said river. So that's also another probably explaining variable for other camps at least.
Okay, another one is saying, great talk, guys. Do you know which of the camps have a recording or have recorded the most complaints from the guests? Or is this equally spread between all camps you sampled?
That's a great question. So as the other group showed us from the trip advisor reviews, I think that the camp that has the most complaints from the ones we surveyed was definitely Lower Sabi. Even when we were doing our sampling in Skukuza, we talked to some tourists who had just been staying at Lower Sabi and then came to stay in Skukuza, and they said, yeah, there was a lot of bats, but they haven't been seeing a lot in Skukuza, which was interesting because Skukuza was the worst camp that we served. I'm sorry, Lower Sabi was the worst camp we surveyed, and then it was Skukuza. So I think that it is Lower Sabi by a long shot.
Okay, and then this is like a follow-up question. Do you have an idea of the cost to sandparks in terms of revenue from tourism, guests demanding refund, negative reviews, etc., due to bad presence in their houses? How does this cost compare to the cost of implementing these measures that you have suggested, controlling the bats in the camp?
That's a great question too. All great questions, guys. So I think with this question, we do know that I don't know the specific answer to it, but what I can say is that sorry, can you repeat the first part of the question? I'm thinking about the second part now.
The first part is, okay, do you have an idea of the cost to sandparks in terms of revenue from tourism, guests demanding refund, negative reviews, etc., due to bad presence in their houses? How does this cost compare to the cost of implementing these measures you have suggested in controlling bats in their camps?
Thank you. So in terms of like from the reviews we've been reading and hearing from sandparks management, not only are people demanding refunds, but they've booked like a length of stay, and so they can't stay there anymore. So then they're have to relocate it to other camps as well. So that's a huge cost in terms of not only refunding guests, but also moving them. And again, I don't know the specific answer, but I think that if it has to have at least some equal, if not less of a cost. If not, then sandparks wouldn't be considering it.
Very small addition to that. Wonderful answer, Janet. Thank you. I was also going to add that the bat boxes, at least in Bergendal, were set up by volunteers, and they are not being paid to do that work. So that definitely factors into the cost. I don't know how much proportionally, but I just thought it was a small little detail to add. Oh, we have one more question.
Hi, guys. This is just a curious question. I know the river distance did not make any significant impact, but when you did river distance, did you do it the whole camp or at each accommodation?
We looked at the distance between each individual building and the river. And so what we think is that the whole camp is pretty close to the river in all of these cases. And so the difference between one building and another probably was not a big enough difference to make a difference for bats.
Thank you.
Thank you. Thank you so much, guys. We are now going to move on. We're moving away from the mammals and delving into the world of grass and fire adaptations. And Porter, Marshall, and Mary Thomas are going to tell us more about grass leaf sheaths and crown depth and the adaptations that they might have in granitic and basaltic soils. Okay.
Thank you. Hello, everybody. My name is Mary Thomas, and I go to Colgate University.
Hi, and my name is Porter Comstock, and I also go to Colgate University.
And I'm Marshall Mumford, and I go to Cornell University.
And today, we are going to be talking to you about grass defenses against fire. Okay, so a little bit of background about savannas. Savannas are defined by the tension between C4 grasses and woody vegetation. And one way that these plants stay in balance is due to disturbances. And savannas are disturbance-driven systems, and one of those disturbances is fires. So due to this, grasses have developed various traits to defend against fire, including avoidance, resistance, and tolerance. And today we will be talking specifically about resistance traits, which is basically the grass is trying to minimize how much is being burned to be able to bounce back after these disturbances. So one trait that we were looking at is leaf sheath thickness. Previous studies have examined how leaf sheath packing can serve as insulation for grass in terms of fire, but they haven't looked at how the leaf sheath thickness influences this. And so when we were in Sawney Pass earlier this semester, we found that leaf sheath thickness can influence the insulation that grasses are experiencing during fire. And so we're interested in continuing this survey, as Liesl mentioned earlier, and seeing how the grasses respond in Kruger. And one really important thing is you can see in this figure that the little lines represent the sheaths, and the grass is trying to protect the basal meristematic region, which is a critical region for growth. And so we looked at Hyperthelia dissoluta as our study species, which you can see right here. And the reason why we use this species is because the culm, which is the stalk part, was thick enough for our thermocouple receptors to fit into. And then the leaf sheaths are the blade-like things that are coming off of it that are wrapped around the culms. Additionally, we were looking at crown depth, which is how deep the crown is beneath the soil surface. And again, this is protecting some of that critical basal meristematic region. And since we're looking at fire, we know that fire can be influenced by a variety of factors, including soil nutrients, soil type, and soil moisture. And so we wanted to specifically look at soil type, particularly because Kruger is dominated by basaltic and granitic soils. And these two soils are different because basaltic has more clay in it and is a lot more finer grain, whereas granitic is more sandy and is a coarser grain. And as you can see, the darker parts of the map of Kruger are the basaltic and the lighter parts are granitic. And so previous studies have not examined the relationship between crown depth and soil type. Other studies have looked at crown depth to some degree, but they haven't looked at how the two play together. Which leads us to our research questions. First, how does leaf sheath thickness affect thermal insulation of Hyperthelia dissoluta? And what are the thermal insulation properties of basaltic and granitic soils in Kruger National Park? And to test these questions, we had two different methods. One was to test the leaf sheath thickness, and we modified culms. So here you can see Porter drilling into the culm so we could put a thermocouple receptor up into it. And then we added 0, 1, 2, 3, 4, and 5 leaf sheaths onto the culms to simulate different thicknesses. As you can see here, we've got the different amounts of leaf sheaths. And then
we had this modified piece of plywood where you can see the little silver knobs coming up are the thermocouple receptors, and the green circles are the receptors that we put the combs onto. And then we had some that were left without combs on them so we could take the average fire temperature. And so then we put the combs onto the thermocouple receptors, and then we lit them on fire, which was a lot of fun. And then after we lit them on fire, we took them off, and we then measured the diameter after we burned them, because we measured the diameter before and after to get the thickness. And then for our soil treatment, we had an experimental burn box, which we put basaltic and granitic soils in. We had 6 burns in each soil type, and in each burn, we had 12 receptors on the surface, which are represented by the letters on the screen. And then we had 12 receptors at depth represented by the numbers. And you can see that we triangulated the surface temperature around the receptor at depth, so we could get an average surface temperature compared to the receptor at depth. And then we had 2 burns at 20 millimeters, 2 burns at 30 millimeters, and 2 burns at 40 millimeters for each soil type. And you can see here, we modifying the box to drill holes in the side. You can see Sia underneath sticking the receptors through. This is me lighting the grass on fire. And then here's the box on fire. So you can see we have the experimental box with then the grass burning on the inside.
Oops. Okay, let's hop into some of these statistical analyses. So as mentioned, one of the traits that we studied was leaf sheath thickness. And so what is leaf sheath thickness and how do we calculate that? So on the left side of the screen here that you can see in that photo, we have a culm, which is just an internode of that stalk that you saw. And we took the diameter of the culm with the leaf sheaths. And then after we burnt that culm with the leaf sheaths, we then removed that leaf sheath, and then we calculated the diameter of the culm without the leaf sheaths. And then we took the difference between those two measurements, and we then divided that by 2 to get 1/2 of the thickness of the leaf sheaths around the culm. So obviously we're looking at leaf sheath thickness, and you're wondering, well, how well does leaf sheath thickness insulate the culm from fire? Insulation is just the difference from the external culm temperature from the internal culm temperature. And we found a strong positive relationship between leaf sheath thickness and insulation, found an R-squared of 0.949. And we found that with every millimeter increase in leaf sheath thickness, there was an extra 6.1 degrees Celsius of thermal insulation provided. Yep. So that's leaf sheath thickness. Now on to crown depth and soil type. So here we're comparing between basaltic and granitic soils. Insulation is the difference between the surface temperature and the temperature at the sensor depths. Do I remember it's 20 millimeters, 30 millimeters, and 40 millimeters? And we found that granitic soils offer significantly more insulation than basaltic soils. And we also did this same statistical analysis at each depth. So you compared each soil type at 20 millimeters, 30 millimeters, and 40 millimeters. And at every depth, except for 30 millimeters, we found that granitic soils offer more insulation than basaltic. The 30 and 40 millimeter, or sorry, the 20 millimeter and the 40 millimeter depths highlighted in red there. We're also curious about the exposure to lethal temperatures that these plants might encounter in the field. The literature suggests that the threshold for lethal temperatures is 60 degrees Celsius. So we wondered, well, how many of these fires at depth reached temperatures greater than or equal to 60 degrees? We found that there were a total of 4 fires that at depth reached temperatures at this threshold. 2 were at granitic at 20 millimeters, and then another 2 were at basaltic at 30 millimeters depth. We found that the fires that for in granitic soil, temperatures at depth were spent about 40 minutes at 60 degrees or Celsius or greater, whereas basaltic spent 155 minutes at this lethal threshold. Then we wondered, okay, well, how long does it take for each of these soil types to cool from their peak at or above 60 degrees Celsius back down to 45 degrees Celsius? And we found that it takes almost 3 times as long for a basaltic soil to cool than for a granitic soil to cool when it's maximum temperature. When you visualize that here in this graph, this is a graph of granitic soil reaching its peak temperature and then cooling. This is a very, very quick pulse of fire through the soil here. Now, this is a comparison. On the right-hand side, you can see the granitic soil. You can see it reaching its maximum temperature and then it cooling. And on the left-hand side, you can see the basaltic. They both have this, rather quick, increase in temperature to its maximum temperature, but the basaltic remains at this lethal temperature for a longer amount of time than the granitic. And you can also just watch as that slope decreases. It's much steeper for the granitic than it is for the basaltic. This is really important in how well plants at that, crown depth of that depth can sustain temperature and survive. So
our major finding was that granitic soils did provide better insulation than basaltic. And we also found that the granitic soils reached higher peak temperatures during our fire and cooled faster, while basaltic soils retained lethal heat longer. So it kind of opens the door to future research into, does a grass want to be cooked very quickly, or would it rather sort of sit at closer to 60 degrees for longer? And we may be able to explain the differences in soil properties and correlate it to our differences in insulation. Granitic soils, like Mary Thomas said at the beginning, are coarser, they're a lot sandier, and they leave an opening for air to fill in holes, whereas basaltic soil is very fine, it's very clayey, and spill it on the ground, it makes a big plume of smoke, and that's going to fill in every crack that you have. It's going to sort of close in these air pockets. And so as heat travels down, it's going to be traveling from particle to particle in the basaltic soil, whereas there'll be sort of these openings and tunnels and pockets of air for heat to travel through the granitic soil. And as our leaf sheaths go, we found that thickness and culm diameter were positively linked to better insulation. Our findings support existing hypotheses that thicker or more leaf sheaths help protect grasses from fire. And it may tell us something about the intensity of fire that a grass is adapted to. So if you find a species of grass in the field that seems like it has an unnecessarily high amount of leaf sheaths, biologically that may be serving as a protection against fire, or it may be providing better insulation. And so some management implications for sandparks. Currently, the fire strategy attempts to promote palatable grasses and also resist woody encroachment. And so we're looking at palatable grasses species like Panicum maximum in the field. And if you sort of look at it perhaps at a species specific level, you look at the biology of the grass that you want to promote and also the woody encroachment that you're trying to resist. So by looking at the leaf sheath thickness and also taking into account the soil type that you're burning in, you may be able to modify your fire plan more specifically to a species of grass or a type of grass. So by saying maybe this grass could withstand hotter fires because it has more leaf sheaths, because it's deeper in the crown is deeper in the soil, or because it's in a different soil type, maybe you can burn a hotter fire and get a more favorable outcome. And so for some future research, we suggest comparing leaf sheath insulation and crown depth insulation between different grasses in the different soil types in Kruger. We also suggest looking at the soil insulation part of our project in an experimental burn plot. So because we did have to shovel dirt and bring it back to the SSLI campus, we sort of removed that organic subsurface ecology that's going on. You're removing crystallization that's occurring on the surface, sort of natural processes, and instead you're just looking at the soil. So if you are able to put thermocouplers within natural soil, you would be getting a more realistic view of what's happening. And also refining burn models by incorporating leaf sheath thickness, crown depth with existing model components like humidity and temperature.
Thank you for listening, and thank you to our wonderful game guards, Kazamula and Thomas, and to Dr. Gareth Hampson for his insight, guidance throughout the project, and of course our project advisors, Sia and Lisa. Do you have any questions?
Oh, I think we've got many questions, burning questions.
Yes,
Group?
absolutely.
For incorporating these new measures into current existing grass measures, our biggest problem both in Sawney Pass and I'm sure for you guys here was finding grass culms thick enough to get the thermoreceptors into. How would you recommend incorporating that if the grass is not thick enough to get the receptors?
Yeah, good question. So I think we think of Hyperthelia dissoluta as an experimental species, something that's fairly common, maybe in more, higher rainfall areas possibly. So it's not necessarily representative of all grasses, but what it does have is that it has leaf sheaths and that it's discussed in these fires where it's maybe more burn prone. But I think how this can be translated to other grass species is going in the field and measuring leaf sheath thickness of different grass species in the field and getting a understanding of how leaf sheath thicknesses vary between grass species. So I think this is just saying leaf sheath thickness is important, and there's clearly a relationship between insulation and thickness. Let's go in the field now and see how those thicknesses vary in the field.
Hi, I know the grass species that you used for this experiment, was it found both in basaltic and granitic soils?
No. When we went into the field, we found Hyperthea dissoluta only in the granitic sites. Pretoria Scop and Stevenson Hamilton. We traveled to Lower Sabi. We did not find any Hyperthea.
The literature suggests that it's out there in both sites, but when we actually in practice went out to go find it, we couldn't find it in Lower Sabi. However, there have been instances where it's been found. But the idea with using it in this case, kind of like Porter just mentioned, was to prove just in general that leaf sheaths can influence insulation. And then, like you said, you can then apply that to other grass species and other experiments.
Okay, and just a curious question, when you were in the field, now that you know that granitic and basaltic have different insulation capability, the swells, did you see any differences in the leaf sheaths of the grasses in the field between the two sites or the two swells?
That's a good question. I feel like anecdotally, I didn't notice a difference. I don't know if either of you guys did, but we also weren't spending a ton of time examining the grass closely in the field because it was more of an experimental study. But I think it would be interesting to go back out on that.
Thank you.
Great piece of work. So when we compiled that trait handbook, a lot of it was ideas, and so it's phenomenal that you guys are actually testing some of these things now. So a couple of questions. The one is so I'm intrigued by your soil stuff, and soil becomes really important for not only grass survival, but also woody rootstock survival, but also interesting things like how deep a seed needs to be buried by a squirrel for the marilla to survive and germinate. So I think yours is probably the first work that I've seen from soils in this part of the world. So already that's amazing. But how did you measure the soil insulation? Because I'm really struggling to wrap my head around the basaltic soils being lesser, because granitics are more porous. You'd expect and your data would suggest that there's the slope was steeper, therefore it accumulated heat faster. So how did you measure insulation capacity?
So we took the average maximum surface temperatures and we subtracted the average maximum surface temperatures from depth from the ones at surface, right? And so we said, okay, at 20 millimeters it was this, at 30 millimeters it was this, 40 millimeters. What we didn't take into account in this preliminary analysis yet is that there were differences in maximum surface temperatures of the fires. That does play a role in how hot the soil is and how much heat can actually penetrate the soil, how far it penetrates, and how long it lingers. So in future analyses, we want to incorporate, maximum surface temperature into our models. But right now, just for these preliminary analyses, we're just measuring the difference between the temperature that we're experiencing at the surface and the temperature that we're recording at depth. Does that make sense?
Yeah.
Okay.
And so part of that then would also be, so obviously you standardize amount of biomass you're burning, but the effect of the fire will be both a product of the mean temperature and the residence time. So it'll also be interesting to know how long your grass biomass is burning for. Anyway, so these are all technical, wonderful questions that, down this rabbit hole of this fire stuff.
And to your point, we also thought about designing a different experimental study where since we have 12 receptors, 3 depths, we have, groups of 4 receptors, each at 3 different depths. So then we have the same surface temperature at the surface, but it'll also be interesting to measure residence time as well. Yeah.
So we cheated with the woody stuff. What we did was we put out all these intensity Actually, if I told you what you already did. So you drink a lot of beer and you pour and then you put 50 mils of water in a beer can at 3 different heights and put about 100 of them in the landscape. And then you burn through with a medium intensity burn and you look at how much water is lost. And then you come back and experimentally burn to try and calibrate that same amount of water lost. And that becomes like a standardized fire effect. And so, because that takes all the guesswork out of how much biomass is burnt and residence time and all kinds of good stuff. And so there are all kinds of workarounds. Anyway, so what's really fun about your work is it's brand new. Like the bad stuff, we out to see, and that's the joy of your capstones is we're having fun cracking it down there. Amazing.
Thanks. I'm going to have to stop following Lawrence because I have to keep checking off all the questions as he asked them. But I'm curious a little bit about how you did the soil. Can you go back to your last, kind of lessons learned, the previous slide? Yeah, this was great, by the way. Keep that up. Yeah. So future research, I think this is wonderful to always include it because it's a little bit of lessons learned that you had. So one of the things that I was quite thinking about as you're giving this talk is, when you gathered your soil, did you try to maintain the profile at all? Or, did you kind of mix it? And then once you put it back did you actually look at soil moisture effects? Okay, great. I'll stop there for a second.
So we did look at soil moisture. We collected it before we burned, and we dried it, and we found that it was both were less than 10%. So we were told that is not a significant amount of moisture in the soil to drastically change the results. And during collection, unfortunately, both of these soils in the landscape were quite tough to dig up. And so there was a lot of hammering a shovel into stubborn ground, and we had quite fragmented pieces. So we were not able to sort of cut like a piece of cake out of the landscape and take that home with us. We did end up with a lot of chunks and a lot of fragments. And so I think when we got back, we did our best to sort of standardize it. We didn't have clumps on the bottom and fine soil on top. Like we did mix through the soil just to make it sort of the same across the depths, but it wasn't reflective of what we saw when we were digging it up at all.
That's really great. As I was driving through the park yesterday, I had lots of questions about, I know they're doing some prescribed burns, and do you know how they're doing them? Are they using different seasons? Are they measuring the fire load that's on there? Because there's a lot of woody encroachment in areas, and are they studying this at all? And I'm just curious if you can kind of address that and see how that might play with your future research.
Yeah. So Kruger has a ton of experimental burn plots that have been in place, I think, since the 1950s. And so they have been studying this. We weren't looking super extensively at it. Although we did talk to Tertia Stridham, who is one of the fire ecologists here, and she was also kind of able to help us get a little bit of insight into that. But I guess the big general answer to your question is yes, they're doing studies on it, which is also part of our suggestion of implementing this in the burn.
And there was also an interesting study too that was looking at, it was between soil types, and they're looking at, fires at different times of year and then different fire intensities. And then they were measuring the relative frequency of different grass species. And they found that Panicum maximum had the greatest relative frequency in the unburned plots. Then Hyperthelia dissoluta was, I think, the greatest relative frequency in the intermediate burn plots. And they went species by species. So, if you then go in the field and you count, okay, on average, Hyperthelia dissoluta has this, has this leaf sheath thickness. Panicum maximum has this, like Eurocloa, Mozambica census or whatever had this much, right? Then you can say, okay, model that and say, hey, if we burn it at this hot of a fire, then we know it's going to regenerate at this rate or something. That might be possible, but yeah.
That's great. Thank you. I appreciate it.
Thanks, guys. Yeah, very, very cool to see just experimental work like that again. It's really nice. And just out of interest, when you you mentioned the insulation properties or the thermal conductance of the different soil types and how they're different between basalts and granites. Did you come across similar work in the literature? Were there any sort of general guidelines around what what influences sort of heat conductance in soils? The key characteristics?
The literature that I looked at for sort of heat, it was talking about like heat diffusivity and heat conductance was, it wasn't talking about maybe granitic and basaltic directly, but it was talking about the composition of the soils. So if you have like a sandy or a loam and sort of how that is going to impact where and how quickly your heat's moving. And I wasn't able to find anything directly for Kruger on sort of burning the soil, but we also found experimental studies that use ovens to burn heat into soil. And there were, well, Porter can talk more about this, but the results for that were different than what we found. But you do sort of have to balance like an oven and the kind of heat that it's producing and the way that it's producing heat versus the fires that we lit in a more realistic manner, albeit in a plywood box, but better than an oven, I would say, in comparing the grassy biomass.
In 2009, I did this, and this is in an oven, and they said they set the temperature to 700 degrees Celsius, and they set it for 660 seconds. So that's only what, like 11 minutes. So, whereas our fires, we let them burn for 2, 3, sometimes 4 hours, and we would find that after 2 hours, sometimes, like usually in basaltic, the maximum temperature would be recorded after 2 hours. So if you're only burning it for 11 seconds, so anyway, there is some prior literature. They did find some different results than us. They found the opposite, but yeah.
Also, our fires burning for 4 hours, it wasn't an active flame for 4 hours. It was an active flame for maybe 20 seconds. Like as we lit it along one side of the box and allowed the fire to just naturally move through it, and then allowed it to cool for 3 or 4 hours, which is when we were getting the maximum temperatures.
The heat is going to descend down the soil column, and some of those haven't done that yet. So,
Sia, do you have any?
Richard, what are the grasses used for? Grazing for animals?
Yeah, that's a good question. So Kruger is a Big Five game reserve, and so part of their management strategies are to preserve some of these large animals, and one in particular that we discussed is rhinos, and they prefer certain palatable grass species. So, for example, you could be doing some sort of prescribed burn that's targeting palatable grass species for species like rhinos.
Okay, the second one is from Levy. You touched upon the cooling properties of the soil when you talked about the density of basaltic versus granitic soils. But do you think the atomic differences in mafic and felsic soils play a role in the cooling time? The felsic and the mafic.
My knowledge, that's where my knowledge of soil types ends. It's above my pay grade, but I don't know. I think it'd be important to think about the crystallization of the soil, like Marshall's talked about. Think about the porosity of the soil. I can't speak to those soil types specifically.
And also, I think that part of the goal of this study is to design management strategies for Kruger, and so we're comparing the basaltic and the granitic and the properties kind of associated with that in Kruger, and those fires.
And I did read a paper on how soil changes atomically after fire burns over it. And there was literature to suggest that it sort of becomes more water repellent, becomes harder to sort of penetrate the surface beyond crystallization, like you'll have higher runoff. So there are changes that occur as the soil gets burnt in both of our soil types that we couldn't really look at with ours. Despite repetitively burning it, we didn't find any significant differences in how the soil was changed. So.
Okay. We've got another question from Tom. How does soil organic matter differ in the horizon between the two soil types?
That's a good question. It's something that we didn't look at in the different soil horizons for this study. Kind of to Marshall's point that we just it ended up getting pretty mixed up, and we also weren't looking at the organic material.
Okay, second question, same from Tom. Do available soil nutrients differ between the two soils?
That's also a good question and something that we didn't look at with this study.
Okay, third question. Can you comment on how biomass and associated feedback of transpiration impact?
Yes, to kind of address the biomass question first, originally we had designed our experiment to have varying levels of biomass to see how that influenced the fire intensity. But when we burned the highest amount of biomass that we had found in the field, the fire temperatures just were not getting quite hot enough. So then we modified our experiment and just burned a standardized 1 kilogram of dried grass across all of the fires. And so we also weren't looking at the transpiration of it because the grass was dried in this case.
Yeah, I don't know if they're asking about like the soil moisture or the content like with grass growing in it, like the transpiration from the grass is affecting soil moisture affecting the soil moisture or not. But we rather, I don't know if it was the same day, but maybe a couple of days after we collect the soil, we gathered it and we dried it. So I don't know if that's what they're asking. It's hard to say to answer that question, but we did account for soil moisture.
Oh, was the last one.
Okay, thank you very much, guys. We are now going to be moving on to our last presentation. Sorry. And I'm going to welcome Natalia, Koketso, Marvelous, and Perry, and they're going to be talking about the top-down and bottom-up controls of the Swazi lily.
Everyone, today we will be talking to you about the role of top-down and bottom-up forces in shaping the survival of Adenium swazicum in Kruger National Park. Hi, I'm Perry, and I'm from Emory University.
Hi, my name is Koketso, and I'm from Wits University.
Hi, I'm Marcus. I'm also from Wits.
Hello, I'm Natalia, and I'm also from Emory University.
Okay, our study species is the Adenium swazicum, which is a perennial succulent shrub that has broad leaves, thick stems, and pink flowers. This shrub is well distributed in South Africa, Eswatini, and Mozambique. It is currently vulnerable. Okay, so the Swazi lily, which is its common name, is currently declining in Southern Africa. Many of the reasons for its decline are anthropogenic, including habitat destruction, habitat disturbance, and being harvested for traditional medicine. However, the species has also been monitored in Kruger National Park for the past 15 years, and Sandparks has been noticing a population decline in this protected area as well. So we're looking at some of the top-down and bottom-up controls that might affect the Swazi lily. So some of the bottom-up controls include soil moisture, pH, and salinity, while some of the top-down controls include herbivory and trampling. However, these controls are very interconnected. For example, higher soil moisture or a water source at sites may increase mammal occupancy, which then mammals deposit fertilizer, which would increase the nutrient content of the soil, which makes it even more attractive to herbivores. So these processes have many like cyclical parts, and so that's why we're kind of studying both the top-down and the bottom-up factors. So our hypothesis for the bottom-up factor is that higher salinity and higher pH, and both of these are connected to nutrient content in the soil. And since Adenium swazicum prefer nutrient-rich soils, predict that higher salinity and pH along with higher moisture, which allows for the emergence of seedlings because they can break through the soil easier. All of these factors being higher will increase the reproductive success and the growth metrics of the swazi lily. For our top-down controls, we hypothesize that increased animal activity, either through herbivory or trampling, will decrease the reproductive success and growth metrics of the swazi lily.
So, our site took place in Kruger National Park, and it was in the southwestern portion in the Malelane section. As you can see in the graph, we had 4 study sites, and they were at the very border of the park. So our landscape was characterized by mountainous outcrops and music savannas, and there were sodic soils with dense grass communities, which was very attractive to herbivores. And we also had some dispersed broadleaf trees, such as the Euchlea divinorum. And our study sites, we had 4 pre-established study sites that were previously used in research and monitored by the sandparks to monitor the health of the swazi lilies.
The health of the Adenium swazicum was characterized by two matrices. The reproductive success, which was represented by counting the total number of flowers, buds, and sepals, and the growth matrices, which were represented by the total number of stems, the stem diameter at the base, the plant height, and the width. So soils were collected at 2 sampling points, at the Adenium swazicum and also at the base of the Euchlea divinorum. So this means that there was a total of 160 soil samples, 40 from each of the 4 sites, and these were placed in bottles and sorted by site for chemical analysis.
So to assess animal activity and presence, we utilized 2 observational methods. One was passive and one was active. So the first one we did was camera traps, and we set up 6 camera traps per site, and we had 3 camera traps on one transect line, and then 20 meters later we have the second transect line. And these cameras were set up either using the stands or the vegetation, depending on the structure of it. And these cameras were set up for 6 days. And then our second observational method was utilizing dung surveys. And with this, we had 4 surveys per site, and they were within the area of the camera traps. And we had recorded dung within a meter left or right of the transect survey. And then we identified the dung based on characteristics such as color, size, shape, and such. And then we also grouped insulate together, such as Impala and Waterbuck, for simplicity.
Soil moisture doesn't seem to have an increasing or decreasing pattern across the sites. However, it seemed to the highest soil moisture, the most saturated soils were seen at site 3. So this is interesting because this happens to be the site with shorter and narrower plants. So in terms of salinity, there's a clear increasing pattern across the sites, with the 4th site having the highest salinity across the sites.
So a linear regression model that we ran indicated that reproductive output or reproductive success of the adenium was weakly related to all of the soil properties. So this is interesting because we can see that taller and wider plants were seen at the fourth site, which happened to be made later.
Overall, our findings in terms of salinity and soil moisture seem to reflect the biology of succulents that have been done. Previous studies, the biology of succulents as has been done with previous studies that in wet sites, which is our site 3 that has the highest soil moisture, succulents tend to be narrower and shorter so that they do not take up a lot of water. And then in dry sites, which is site 4, they tend to grow taller and wider as they are adapted to semi-arid environments. So that is the environment they thrive in.
So for our animal presence results, we found 856 dung observations across the 4 sites and 516 individual animals pictured. And the table shows the distribution of samples throughout the site, and together we were able to find 13 distinct species. And here we have pictures from the camera traps, and we saw a lot of impala, a few hyena, lots of hippos, and some rhinos as well. And then for our results, we were able to determine that the average dung across the 4 sites was significant, and site 3 in particular, in comparison to site 1, 2, and 4, had a higher average than those sites. And the camera trap data, unfortunately, was insignificant. So then moving on to the species by dung, we found that antelope and buffalo were significant, and they had site preferences based on their dung. And then connecting this back to the Swazi lily, we ran correlation tests, and we were able to determine a negative relationship between dung and the growth metrics and reproductive success. So as dung tended to increase, we saw in the plant height began to decrease, and the plant width as well as the plant reproductive output. Plant height had the strongest correlation, and plant reproductive output had the weakest, but they were all statistically significant.
Please remember that site 3 is the site that has the highest soil moisture, so it's a wet site. Therefore, it has a lot of vegetation and supports grazing lawns, which attract a lot of herbivores. That's why it has the highest animal activity. And also in site 3, we saw that with highest animal activity, the reproductive success and growth output of the plants tends to be lower. That is because the herbivores tend to indirectly affect the Swazi lilies, either by laying on them, which we saw in some of our camera traps, or trampling on them, or some studies have shown that herbivores tend to munch on these Swazi lilies during dry seasons, as there is nothing else to eat. So in our conclusion, our study reveals that the decline of the Swazi lily in the Kruger National Park is because of a complex interplay of both bottom up and top down interactions. So for future studies, we wish to implement exposure experiments where we want to entangle whether it's the top down or the bottom up controls that affect the decline. And we also want to look at this seasonally to monitor the seasonal variations in soil properties and also in herbivores. Also, because we only investigated the below ground traits of the Swazi lily, for future studies, we want to look at we investigated the above ground traits of the Swazi lily. For future studies, we want to look at below ground traits to better understand the resilience mechanisms of the Swazi lily. And for our conservation and management implications for sandparks, for future management strategies, they should consider both habitat quality and herbivore pressure on the current sites of the Swazilili. And for their conservation efforts, they must concentrate more on the wet sites, which is where the Swazililis are more physiologically vulnerable and where animal activity is mostly concentrated. Thank you. This is our references and our acknowledgements. We wish to thank everybody who contributed to the success of this project. And most importantly, we wish to thank ourselves. Thank you. Okay, now that you've thanked yourselves, do we have any questions for this group?
So you mentioned that these factors are playing a role in the decline of the Swazi lily. How have these factors, if you know, changed over time as this plant is decreasing over time?
So one possibility with the animal interactions is, since Kruger National Park is fenced and enclosed, animal densities have been different here than in an open system. And so, for example, we've seen potential problems with elephant overpopulation, along with, we found a lot of significance with impala being super concentrated at that site 3. One of the management implications of Kruger is that impala have been increasing in population size a lot. So it could be that change that's affecting the Swazi lilies.
Also, in terms of the soil properties, fewer studies have actually looked at the soil properties because they also don't want to they don't want to put the Swazi lily at risk by affecting its microclimates. But what we have done is just like a stepping stone, because we only looked at 3 soil properties. They could look at soil physical properties and also like biological properties, such as if there's any microbial activity, and we can maybe include that into the analysis.
Thank you.
Very nicely done, guys. I know this was a lot of work that you put in, a lot of hours, a lot of digging, a lot of soil. Do you think it would be worthwhile doing an experimental study looking at different soil properties if you can access or grow Adenium swazicum and then look at soil properties and egg growth?
Yes, I think it would be valuable to actually build a soil profile that the swazicum prefers. So like I said, we only considered 3 of the soil chemical properties. Other studies could look at the influences of physical properties such as soil texture, bulk density, and when they have also we were supposed to do soil organic carbon, but due to unforeseen circumstances, we couldn't. So other studies could include that too. And once, it would be good if it's an experiment, because now they have a baseline of how they prefer it, and then they could just implement it in the field to see how it reacts in real time. Yeah.
Nice piece of work that looked like a lot of effort with all the soils. So I think your suggestion around exclosures is a really neat one. And so fortunately for us, we've got a whole bunch of camps where they are found naturally. So that might be one sort of low-hanging fruit, to look inside the camps, to look at and some of the metrics that you measure, I thought were really neat. Looking at plant size and reproductive output, I think is such a key one. And so my question is associated with plant resilience. So for many savanna plants, they get absolutely hammered by herbivores, and life is tough anyway, but then you've got this herbivory and the effects of fire. And so the 2 ways in which, well, there are many ways, but 2 major ways in which you can deal with it is, one, you are resilient. So as an adult plant, you kind of tough it out and then reproduce in the quiet times. Or the other is to reproduce and produce lots of seedlings. And so did you guys see any evidence of seedlings or small individuals in those populations as an indication of regeneration or reproduction?
Unfortunately, we do not see any.
I would actually pay you a lot of money if you did. And so that's the fun part around what you guys are doing, is the effects of herbivory and fire are extraordinary. and overlaying that on top of the bottom-up controls that you guys have explored so neatly. And so part of the exclosure stuff would be not only to see the release from herbivores, but also look to see if these things are producing seedlings or not. And that's one of the giant mysteries. The argument is that these succulents are pretty robust in the face of climate change effects and so on, but it'll be very neat. But just great piece of work. And, you know, unfortunately, work like this always big. You ask further questions. So the point is, are you going to come back and engage in that?
Maybe sometimes, like she said, we only look at the above ground stuff. It would be interesting to see what's happening below ground. If there's any like interesting interactions and which markets are there. Also, if it wasn't evident, we took soils from the Swaziland and from Lucia de Valorum because they are known to grow in close association with each other. It is just unfortunate that there was no like significant difference in their soil properties, but there might be some differences in terms of microbial activity on both the Lucia and the soil. Yeah.
Just to follow on from that, did you find a relationship between, I might have missed this, did you find a relationship between plant size and reproductive output at all?
The regression models that we ran did not seem, it seems that soil properties, all of them does not have a relationship with any reproductive output, number of flowers, buds, or sepals. So, yeah.
Because it was interesting that you have smaller plants in the wetter areas, which may just be related to below ground plants investing less in the root. Yeah, reaching sort of the area, lengths and everything, resulting in just smaller plants all around, and perhaps causing a bit of a reproductive trap in that way. But I'm unsure if that would really make sense. But it's probably the most likely sort of bottom-up factor to have changed in the time scale of the conservation concern. Things like salinity and pH and that potentially are variable, but potentially on time scales are different from what we've seen. Whereas soil moisture is something that can have rapid changes.
Any other questions in the room? Sia, do we have questions online? No questions online. Okay, then thank you so much, guys. I mean, I don't know if I need to thank you because you've already thanked yourselves. So then I'm going to give the microphone to Josephine Pegg. She is going to be wrapping up the session for us.
I shall keep it quick because we've had so many questions. So thank you so much to everybody in the room and everybody online who has engaged so much with our students. They've worked very, very hard. So thank you for listening, and thank you for asking them difficult questions. There are some other people that I must thank also. We are only able to do this work, which is an enormous privilege within the park, by the grace of SANParks. As always, we hope that it is very useful for SANParks, and we can repay the privilege of working here by making work that is of value to them. So a few persons who do deserve a thank you. First and foremost, the game guards, Kazabula, Wilson, and Thomas, because we get in awful lot of trouble when the students get eaten. So cheers, lads, for that. Also like to thank the section rangers, Callie, Rangani, Marius, and Wilson, who have facilitated our work within their areas. We've been out and about in our little cars, and they've been keeping tabs that make sure we're safe out there. From the BAT team, thanks to the camp managers and the hospitality staff, I must say that the ladies who clean have been engaged in a battle with our students, because the rate of cleaning versus the rate of monitoring bat guano was a race against time, and they are efficient. Thanks also to Sean at Lukimbi Lodge. Lukimbi Lodge continues to let us go down and look at their Swazi lilies, which is very generous of them. Our thanks to the researchers, our Sandparks researchers, Corley and Stephen, and to Gareth for inspiring this work that has been done. They really did set some tough challenges, and I think you chaps really rose to the occasion. And then last of all, in the words of Kaketso, thanks to you guys for doing the work. Yeah, this is it. This is it. The end of the road, really, academically. For now, for the class of spring 2025. You have been an absolute pleasure, both in terms of good work and good vibes. So Lawrence is now going to put a lot of time and effort into luring you all back. So resistance is futile. Come back, do some more work, and thank you all very much indeed. That is all.
Okay, thank you very much, everybody. We are now gonna head off to have some tea, which should be right outside. We'll just check because we are running an hour behind schedule. But yes, thank you so much, and see you there.